Hello, Chemistry 20. This is our 10th lesson in the Quantities in Chemical Reactions unit. This is limiting and access reactants. In this lesson, we will explore the concept of limiting and access reactants. Then we will look at how to determine the limiting reactant of a chemical reaction. Then we'll move forward with 3 examples. Consider the following. How many hot dogs with buns can be made from the supplies below? What supply dictates the amount of hot dogs with buns produced? Pause the video and attempt this example. If we think about this in terms of a chemical equation, the hot dogs and the buns are reactants. We have 5 hot dogs and 4 buns. So as a result, we can only produce 4 hot dogs with buns. This amount of product produced is dictated by the limiting reactant. And in this example, that would be the buns because there's only 4. As a result, there would be 1 hot dog left over that did not react. That would be considered the excess reactant. It requires both reactants to produce the product. Therefore, the moment one of the reactants runs out, the chemical reaction stops and we can no longer produce products. In most chemical reactions, one reactant will be completely consumed before the other. As stated, when the limiting reactant is consumed, the reaction stops. The limiting reactant is the reactant that is completely consumed in a chemical reaction. The excess reactant is the reactant that is left over once the reaction stops. Determining the limiting and access reactant. Step number 1, write a balanced chemical equation. Number 2, determine the amount of moles of each reactant. Number 3, using stoichiometry, determine the amount of moles of the same product each reactant can produce. This means we will have 2 sets of calculations. The limiting reactant will produce the least amount of product. This would be theoretically the maximum amount of product that could be produced. Number 4, from the calculations performed in step 3, determine the limiting and access reactant and complete the question. There can be a variety of different questions that require a limiting and access calculation. Example number 1. What mass of water is produced when 2.00 grams of hydrogen gas reacts with 3.00 grams of oxygen gas? Pause the video and attempt this example. First, let's use the Chemistry 20 calculations chart. Remember, we are going to have 2 different sets of calculations, one on the top and one on the bottom here. We need to first start with the mass of each reactant. So here will be the mass of hydrogen gas, and here will be the mass of oxygen gas. We have to perform 2 separate calculations, one going from the mass of hydrogen gas to the moles of hydrogen gas, and the same going from the mass of oxygen gas to the moles of oxygen gas. Then we have to perform two separate stoichiometry calculations to go from the moles of each reactant to the moles of the same product, H2O. At this point in time, we have to determine what is the least amount of the product H2O produced. This will come from the limiting reactant. At this point, the reaction has stopped. Using the least amount of H2O moles produced, we can then convert that to grams to find the mass of H2O produced if the following substances react. Moving forward with the calculation, we first need a balanced chemical equation. We also need the molar mass of H2 gas and the molar mass of O2 gas. This will be our first set of calculations. We'll start with the grams of H2 gas and divide it by the molar mass of H2 to get moles of H2. We can then perform our stoichiometry calculation using the molar ratio in the chemical equation to find the moles of H2O formed. As a result, from 2 grams of H2 gas, we can produce 0.99 ... moles of H2O. We then have to perform our second set of calculations, but this time we'll start with the mass of O2 gas. We will divide it by the molar mass of O2 to get moles of O2. Then perform our stoichiometry calculation using the molar ratio to find the moles of H2O. 3.00 grams of O2 gas can produce 0.18 ... moles of H2O. We now have to compare the two mole values of H2O, the 0.99 and the 0.18. The least amount produced is 0.18. As a result, the limiting reactant in this chemical reaction will be O2. Theoretically, this is the maximum amount of H2O moles that can be produced, because at this point in time, the chemical reaction has stopped. Moving forward, we need the molar mass of H2O. We can then take the least amount of moles of H2O produced, which was 0.18 ... and times it by the molar mass of H2O to find the amount of grams of H2O produced. Theoretically, the maximum amount of grams of H2O that can be produced is 3.38. Example number 2. 14.0 grams of solid iron and 12.0 grams of sulfur are available for a reaction. Calculate the percent yield if 20.22 grams of iron 2 sulfide was produced. Pause the video and attempt this example. We can determine that this is a limiting and access reactant question because we are given the gram values of both reactants, 14.0 grams of solid iron and 12.0 grams of sulfur. Calculate the percent yield. Percent yield always refers to the amount of product produced. And remember, the actual yield is provided in the question, 20.22 grams of iron 2 sulfide was produced. This is the actual yield. Therefore, we have to use the 2 gram values of the reactants to find the theoretical mass of iron 2 sulfide. We can then perform the percent yield calculation. First, we have to start with a balanced chemical equation. Don't forget that sulfur by itself is S8. We are going to need the molar mass of iron and the molar mass of S8. We can then perform our first set of calculations, starting with 14 grams of iron. We can divide it by the molar mass of iron to find the moles of iron. Then perform our stoichiometry calculation using the molar ratio in the chemical equation to find the moles of FeS, which is 0.25 ... moles. We can then perform our next set of calculations, starting with 12.0 grams of S8. We will divide that by the molar mass of S8 to find the moles of S8. Then perform our stoichiometry calculation using the molar ratio in the chemical equation to find the moles again of FeS, which is 0.37 ... moles. We can then compare the 2 mole values of FeS, and as a result, the least amount produced is 0.25 moles. This is coming from the limiting reactant Fe. We are then going to need the molar mass of FeS, which is 87.92 grams per mole. We can then take the least amount of FeS produced, which was 0.25 moles, and times it by the molar mass of FeS to find, theoretically, the maximum amount of grams of FeS that can be produced, which is 22.04 ... grams. Remember, don't round this value yet. Now, when we move forward with our percent yield calculation, we have the actual yield, 20.22 grams, which was provided in the question, and we can then divide it by our theoretical yield, which we calculated as 22.04 ... grams. We can times this calculation by 100 to get our percent yield of the chemical reaction, which was 91.7%. That is all for the quantities in chemical reactions unit.